for about 15 minutes.
First semester.
Why did you have to run over?
It's like my obesity class, so it's all about like the teachers are lazy.
Is that the nutrition thing? Oh, that sounds like a lot of work.
But the kids are the cutest. The kindergartners, I'm like, I want to like take them home. We keep
But,
I told them, I asked them, I was in love with my kindergarten sister.
did you meet the kid?
Yes. They came on Monday.
All right, let's get started. Okay, so welcome to the review session for midterm 3. So midterm is on, it's on Tuesday, right? So what's on the midterm? We'll talk about that. Practice problems are posted. I need to update those. I'll probably update those like tomorrow morning or something like that. I need to add a few more examples of, I think, defective matrices in the system of equations case. The exam right now is unwritten. I told Davia I was going to write some questions, but I haven't had the time to do that. But I'll probably send some to him tonight, and then he'll probably send like that email about like what sections are covered on like each problem. He'll probably send that either tonight or tomorrow. What else? There's a homework due on Thursday, so just keep that in mind. He didn't like announce it, but it's posted. So, and the homework covers pretty much like everything that's on the midterm. So like it might not be like a bad idea to try to do the homework before Tuesday, or at least look at some of it before Tuesday. So, other than that, any questions before we start? Okay, cool. So yeah, what's on the midterm? I think there's been many Piazza questions about it, but so 8.1, 8.2, 8.3, 8.4, 8.5, 8.9, and then there's also 9.1, 9.2, 9.3, 9.4, 9.5. So this will be my quick overview of what's going to be on the midterm. So I guess the big thing right now is that like I don't even know how long it's going to be, because like if based on like the previous midterms where like, okay, so one of them might be like true false. So okay, cool, right? Probably can only ask like 5 true false problems there. And then so you have 6 problems left. Like I don't think 6 Diffeqs in 60 minutes is fair, right? Especially if you want to make them any like tricky, like any bit hard. So I don't know how the exam is gonna be formatted, but oh well. So okay, 8.1 and 8.2. These are like the intro stuff. They're probably not gonna be on the exam. They're too simple to be on the exam. 8.3 is undetermined coefficients. Undetermined coefs / annihilators. So I think there's a chance these could be on the exam. Generally speaking, we usually will test like the harder concepts, but I mean they're like you should know this definitely. 8.4 is complex value trial. I'd say there's a good chance that this is going to be on the exam. 8.5 is spring mass system, like spring mass, like whatever, like oscillations. I don't even know what this chapter is called. I personally don't like it, but hey, who knows? It could show up on the exam. I didn't cover it in recitation, and I think I told my recitation kids to just go read my notes from last year on 8.5, which like 8.5 is essentially like you have all your Diffeq stuff, and then they just slap some new vocabulary on it for different things, and then they just like present it in a different way. So as long as you know the vocabulary for this section, that's good. 8.9, reduction of order. So if you've looked at the practice problems, I'd say like, I think there's like 8 Diffeqs on there right now. I'd say like 5 of them you need reduction of order to solve. So take that for what it is. 9.1 and 9.2 and 9.3. This is just like the intro to system stuff. So if you watch the recitation from today, you'll notice that like these get skipped over real quick. 9.4 is then using eigenvalues, eigenvectors. To solve systems of differential equations. I'd say that's a pretty fair shot. And then 9.5 is what he introduced yesterday. And these are defective matrices, systems. If you came to recitation today or this morning, you would have seen that I had a lot of enthusiasm for these kinds of problems. They're a can of worms that he probably shouldn't have opened up, but I got an email yesterday from him saying that like he told you guys you're responsible for the 2x2 system, which I don't know. We'll take a look at an example like that. Okay, so that's I guess that's what's going to be on the exam as an overview. Again, he's going to send a more detailed. Variation parameters you're not responsible for it. I covered it in recitation just as like. Hey, here's a different way of solving these types of problems. Variation parameters, I guess, it's very limited because it's limited, or the way I introduced it, it's limited to constant coefficient second order differential equations. So you literally can't use them for anything else. I mean, it's up to you. You can learn it or you cannot. Any other questions? Okay, cool. So let's get started then with the prepared material I have. So we'll start easy. I have 6 problems. We'll see how long this takes. So this is number 1. Oh gosh. Okay, so number 1, it's from a midterm. It's from spring 2018, and it's the following. You have y double prime plus 6y prime plus 9y is equal to 2e to the negative 3x. And the idea is find the general solution. Okay, so I mean, here's the homogeneous, which is the first step that we always look for. Y double prime plus 6y prime plus 9y is equal to 0, right? And if we write it as d squared plus 6d plus 9 equals 0, you're able to factor this as d plus 3 squared. And then, so the homogeneous is y h is equal to c1 e to the negative 3x plus c2 e to the, or c2x e to the negative 3x. Right, so for our homogeneous, I guess I didn't write d equals negative 3 with multiplicity 2. But because we have multiplicity 2, when you have c1, right, you have c1 e to negative 3x, that's consistent with what we have. But your second solution has to be linearly independent from the first one. And in order to create this type of linear independence, we add an x in front of it. And so that's how we get our 2 linearly independent solutions. So this should be nothing new. The next step then is to guess the particular. All right, so we need to guess the particular solution. So if you go up, what's our right-hand side? It's 2e to the negative 3x. Okay, so in this case, yp is equal to ax squared e to the negative 3x, right? And the reason is because we would like to just guess e to the negative 3x, but what's the problem with guessing e to the negative 3x? Yeah.
It's part of your
Yeah, e to the negative 3x or a e to the negative 3x, that's in the homogeneous. And then if we add 1x in front of it, so if we just had x e to the 3x, this is bad because this then is in here, so then we just need to keep on adding more more stuff until we get ax squared e to the negative 3x. Okay, yeah.
So just the general rules always go like 1 by x order.
Yeah, just keep adding x's until
Until it's not.
you're out, you're clear.
Okay, thanks.
Okay, so that's yp. What next? So now, okay, so we want to take derivatives, so yp prime. Here you need to take the chain rule, right? Not the chain rule, the product rule, because you have a x squared, and then you have another x function as well. So how are we going to do this? Let's take, so this is going to be, so I'm just take the a out, and then that way we only have to deal with x squared e to the negative 3x. So this is like 2x e to the negative 3x minus 3x squared e to the negative 3x. Okay, so there we go. That's going to be your first derivative. And then the second derivative, yp double prime, this is going to be a. And now here, the first term becomes 2e to the negative 3x minus 6x e to the negative 3x. Over here, you get minus 6x e to the negative 3x plus 9 x squared e to the negative 3x. Okay, now we plug all this back into the original differential equation, which was y double prime plus 6y prime plus 9y is equal to 2e to the negative 3x. All right, so y double prime is this mess up here. It's a times 2e to the negative 3x, and then these middle terms really combine, so that's like minus 12. E to the negative x e to the negative 3x, and then plus 9 x squared e to the negative 3x. I guess I could have pulled out an e to the negative 3x as well, but oh well. And then what else? So now you have plus 6y prime, so plus 6, and then y prime, here it is, that's a 2x e to the negative 3x minus 3x squared e to the minus 3x. And then plus 9y, which is 9a x squared e to the negative 3x. And that's equal to 2e to the negative 3x. Okay, so you just keep on we just have to simplify the algebra even more. So what do you have? This is, okay, so let's just divide everything by e to the 3x here, just so all the e to the 3 or e to the negative 3x's. So all of those are just going to cancel out. So now what I have is the following. I have 2a minus 12ax plus 9ax squared plus, and then 12ax minus 18ax squared plus 9ax squared is equal to 2. All right, so I divided all those negative 3x's out, and then I distributed all the multiplication. So that's what I get. All right, now we look at like terms. Here's a 12ax. Here's a 12ax. They have opposite sign, so they're going to cancel. Here is a 9ax. Here's a 9ax. Here's a negative 18ax. All right, so those are going to cancel. And we're left with then just 2a is equal to 2. So a is equal to 1. And what does that tell me? That tells me that my particular solution, yp, is equal to x squared e to the negative 3x. Okay, and then the homogeneous, and then finally the general solution is y of x, which is the homogeneous plus the particular solution. And what does that get me? That gets me C1 e to the negative 3x plus C2 x e to the negative 3x plus x squared e to the negative 3x. So that will be the answer to this. Diffeq. Yeah.
What if you have a case where the x or x squared terms don't cancel out and you get like some multiple of a plus some multiple of x is completely constant?
Then you did something wrong.
Then you did something
wrong. Yeah, it should work. I mean, it could be the case where you have like more than one constant that you need to use, right? So I think I did cover that. I like briefly cover that in a recitation case, but it depends on what this is, right? What your right-hand side guess is. So let's say, like, if the right-hand side were 2x e to the negative 3x, right? Then my initial guess would have been a e to the negative 3x plus bx e to the negative 3x, right? But those would have ended up conflicting with the homogeneous, right? Because I have a e to the negative 3x and bx e to the negative 3x. And then, so then I would need to multiply that by like the x squared factor, which we did earlier. And then so we get ax squared e to the negative 3x plus bx cubed e to the negative 3x. So in this case, once you like take all those derivatives and solve, you should only end up with the b, I think. Or you should only end up with one of the, or you can solve for both of them. But it will work out. The constants will work out as long as you set up your guess correctly. So that's like the big caveat is like everything on the exam will work out favorably. So if you see something that like is not, like the numbers don't look really nice, then you probably made some error somewhere. Any other questions? Okay, so let's move on. Okay, so that was just one of the like method of undetermined coefficients kind of ways. I mean, use it if you want to. If the right-hand side did look like this, with the 2x e to the negative 3x, then the undetermined coefficients, that would have been a much worse type of way to go about it. But I mean, if there's time at the end, we can like revisit this case, this hypothetical case that I've put up on the screen. But I'll just go with the program and move on. So number 2. This is from a fall 2017 midterm, and it's the following. Consider the harmonic oscillator with external force y double prime plus 4y prime is equal to 3 cosine omega t suppose, so this is part A, suppose that omega is positive. What values of omega does resonance happen? Okay, so this is like, I know I didn't talk about the spring mass type of problems in recitation, but this is like something that shows up as a spring mass problem. The other one, there's one that showed up on a previous final. It's covered in the recitation notes. Let me just, spring mass, recitation 10, spring 18. So that's where the notes are located. This is like one of the type of problem that you'll see for the spring mass problem is they'll ask you like for some definition of omega. So does anyone know what resonance is? Or anyone read the notes for 8.5? What scenario has to happen for resonance to occur? Any ideas? Okay, so I guess if this problem showed on the midterm, that'd be bad. But the idea is the following. So resonance occurs when essentially like the root to the right-hand side equation also occurs in the homogeneous. So okay, so essentially, right, the right-hand side, it has to come from some, like, right, the right-hand side annihilator has to come from somewhere, right? Or if you think of annihilator, or you can think of just like the gas, the particular solution. So if the particular solution, e to the whatever t, shares the same value as the homogeneous, or the same root as the homogeneous, then you have resonance. So given that definition, can we figure out when resonance is going to happen? Any ideas? Okay, so let's solve for, I guess, the homogeneous first. And see if that gives us any ideas. So, right, the homogeneous, we get d squared plus 4 is equal to 0. D is equal to plus or minus 2i. Okay, and so that means that we're going to get d is plus or minus 2y. So you get c1 cosine 2t plus c2 sine 2t. Yeah.
I think y double prime plus 4y prime.
Oh. Thanks. Yeah. So it's y double prime plus 4y. Yeah, that's a typo. Or I just copied it down wrong. Okay, so given that's the homogeneous, what needs to happen then for resonance to occur? So what should that omega be? Or if you had to guess what that omega had to be, what would you guess? 2, right? Yeah, because if it were 2, then the right-hand side, right, you have that cosine omega t term, then the right-hand side would actually be inside the homogeneous, right? And so the roots would be the same. So yeah, resonance occurs when omega is equal to 2, because then you get this differential equation, y double prime plus 4y is equal to 3 cosine 2t. All right, and this 3 cosine 2t comes from e to the 2it. Right, because if you look, e to the 2it spit out a constant cosine 2t term. Okay, and then since this 2i is in here, then the right-hand side would share a root with the homogeneous, and so that's when we're going to get resonance. Okay? Any questions? Yeah?
Is that a colon or an I after the 2?
That's a 2i.
Okay.
Yeah. Oh, occurs when resonance, I see. Yeah, no. That's just a 2.
Okay.
Yeah, that's a 2.
When you put like the I in the sign,
When do you put it? So for the homogeneous, we kind of just drop the I already, right? But yeah, in general, I mean, e to the 2it is equal to cosine 2t plus I sine 2t. So this is when you put the I in front of the sign. But when we write the homogeneous solution out, we kind of just drop that I. Any other questions? All right, so again, all this would have been really easy if we knew what the definitions were. So that's kind of just like a cheat sheet thing where you just like go and like you write your spring mass definitions down on a cheat sheet because, I mean, I certainly don't remember all the definitions. Okay. So that's just part A. What's part B? Part B is more interesting. So solve the problem, solve the differential equation, I guess. Or how should I phrase this? Solve the initial value problem for the omega above. And you have y at 0 is equal to 1, and y prime at 0 is equal to negative 1. Yeah, that's it for part A, right? It was just to find whatever omega was, right? For what value of omega does resonance happen, and omega equals 2. Okay, so now we have this initial value problem, which is this Diffeq that I wrote out above. So it's this y double prime plus 4y is equal to 3 cosine 2t. Okay, so homogeneous we actually solved in step 1. So now we just have to solve the particular solution. So we need to guess yp. And there's a few ways you can do it. I'm going to guess using the complex value trial method in this case. I mean, I think annihilators will work well because you only have, like, this term right here is just cosine 2t, and it's not like e to the t cosine 2t, right? So you don't have like excess e to the whatever terms. So it's fine just to guess your undetermined coefficients. But in this case, we're going to say that yp is equal to a, all right? And then if you say a e to the 2it, again, that's not correct because e to the 2it, the 2I occurs in the root for the homogeneous, right? So, and if you guess that, you're just going to be guessing the homogeneous, so we got to scale it by not a factor of x, but a factor of t. Okay, so again, we have to plug all this back into the original differential equation. So we just got to take derivatives. Here's yp prime. I got to use the product rule again, which I have as the following. 2i at e to the 2it plus a e to the 2it. And then yp double prime is equal to 2i squared at e to the 2it plus 2i a e to the 2it, and then plus 2i a e to the 2it. Okay, so we should simplify a little bit for this y double prime. And so 2i squared is negative 4 at e to the 2it, and then you have two terms here that you can just add up. So that's 4ia e to the 2it. Okay, plug it in. Yp is equal to negative 3i, or is that right? No, okay. So y double prime plus 4y, right, is equal to 3 e to the 2it. So we had to rewrite our cosine 2t term, right? We took this cosine 2t term and we wrote it in terms of e to the 2it now, because our guess is in the form of e to the 2it. So what is that? Y double prime is the following. It's negative 4at e to the 2it plus 4ia e to the 2it. And then now you want to add 4y. So that's 4 times y, which is at e to the 2it. And that's equal to 3 e to the 2it. Okay. This first term and this last term, they're going to cancel, because they're 4at e to the 2it's, but with opposite signs. So now you're just left with 4ia is equal to e to the, or 4ia e to the 2it is equal to 3e to the 2it. So if you solve for a, you'll get that that's equal to 3 over 4i. Okay, but we can't have the I in the denominator, so we got to rationalize this. So I'm going to multiply the top and bottom by negative I. All right, so usually the complex conjugate of the bottom term. So you get negative 3i over 4. So that's going to be my A. So that's not quite the complex conjugate, but it works. If you multiply the top and bottom by I, like as long as you get that I rid of the I on the bottom. Okay, so we have our A now, so that means Yp is going to be equal to, and there's like night shift on my laptop, so let me just turn that off. I'll make the colors look a little better. So Yp is going to be negative 3i over 4 times e to the, or t e to the 2it. Okay, that's plugging it back into my original guess for Yp. Right up here, a t e to the 2it. So here it is. And now what we need to do is we can't leave the problem in this form because my initial differential equation has nothing to do with i's, right? There are no imaginary values in here. So I'm going to have to find a solution that doesn't contain an imaginary value. So what is this? This is really negative 3i over 4. Okay, so maybe that's not the way I want to write it. Actually, that's fine. So negative 3i over 4t. And then e to the 2it becomes cosine 2t plus I sine 2t from the Euler's formula. Okay, distribute. I get negative 3i over 4t cosine 2t plus 3, and then fourth t sine 2t. All right, and that's because this I and the negative sign multiplied with that I gets me a positive 1. All right, so we're almost done. What's the last step here?
Take the real part.
Yeah, take the real part, right? Because my initial differential equation, the right-hand side is the cosine term, right? So that doesn't mean take the cosine part, all right? That's wrong. If you take the cosine part down here, you have the wrong answer, all right? Cosine, this means take the real part. So if you go down here and we look at what's the real part, well, it's the part that doesn't have the I in it. This part has an I in it, so that's not what we want. And so that's going to be what we want. And then yp is 3/4 t sine 2t. And the homogeneous, or then the general, is going to be the homogeneous plus the particular. So y of t is going to be equal to c1 cosine 2t plus c2 sine 2t plus 3/4 t sine 2t. We're not done because this question asks for the initial value problem. Y of 0 is equal to 1 and y prime of 0 is equal to -1. All right, so now we need to take the derivatives to find the initial value problem. So y prime at t is what? It's -2c1 sine 2t plus 2c2 cosine 2t, and then some trash here, 3/4 sine 2t plus 3/2 t cosine 2t from the product rule. Okay, so now we plug in our initial value conditions, y at 0. Right? So we take that first guy, we plug in 0. So what do we get? We get cosine at 0, which is 1. So that's just c1. And then these two sine terms, right, they're just going to die out from the zeros. Okay, so we get c1 is equal to 1. And then now y prime at 0. Okay, what are we going to get? Well, okay, so y prime at 0, you take this, and now you plug in 0 into the t's here. This sine term is going to not be anything. All right. Over here, we get 2c2. All right, since cosine of 0 is 1. All right, here, sine of 2t, that's going to die out. And then here, 3/2 t cosine 2t, you have this t term right here. And remember, we're valuing the derivative at t equals 0, so that's going to die out as well. So essentially, you get 2c2 is equal to -1. And then this is a really easy system of equations to solve because it's already solved for you. And you get c1 is equal to 1, c2 is equal to -1/2. And then y at t is going to be cosine 2t minus 1/2 sine 2t plus 3/4 t sine 2t. Any questions? Yeah.
Aren't we like rewrote like 3 cosine 2t as 3e2i?
Yeah.
Like in that case, you never need to add like an extra t, even though. Like,
No. So the right-hand side, just keep it like as it is.
So like do like most of these.
Yeah, exactly. Right. Only the guess needs to be modified. The guess is the only thing that ever needs to be modified. Everything else stays the same. Yeah.
So if the only thing, if we had like the original equation equal to 3 sine
Yeah.
wt, the things that would change would be that our guess for the particular solution would be a t e to the -2it.
No. So it'll still be 2it.
It would still be
It'll still be 2it. So even if the right hand side said sine, right? So the question is, what if this said 3 sine 2t, right? So if that's its sine, if you notice, the Euler's formula gives you a cosine 2t and an I sine 2t, so it gives you like the sine 2t part as well, and so you don't guess the negative 2i. Although I think it works. I think it should work, right? But It's just safer just to stick with the positive
So
term.
you never guess the negative.
Yeah, you almost never guess the negative term.
So the only thing that changes is you just take the imaginary.
Yeah, exactly. Yeah.
So when we found A and we had I in the denominator, it's like a general rule that you want to move the I to the numerator.
Yeah, I mean, there's no way. I mean, when you do this multiplication here, if i's in the denominator, you can't do anything, right? Or like, what are you gonna do? I guess it can cancel out like the I and this I sine 2t term, but then you have the I in the denominator for the other term, and then it's like. Any other questions? Yeah.
Sorry, earlier for like part A,
Mm-hmm.
you put like a little arrow down from there, yeah. And you said like it just spits out e to the 2it. What exactly?
No. I said this comes from e to the 2it. So e to the 2it spits out this guy. Right? Because here I wrote out e to the 2it.
And you're just ignoring the natural.
I mean, yeah, more or less, right? Which is why at the end we only take the real part of the solution. Any other questions? Okay, cool. So that's complex value trial there. Let's see, any other comments I have? Not really. Just be careful. So I think the biggest mistake that happens with complex value trials isn't even the algebra during the complex value trial part, because I think what happens there is that everyone's like, oh shit, I need to like keep track of these i's, and like that generally like goes well. What happens is people factor this guy and they factor it as d plus 2, d minus 2. Well, don't do that because what happens then is that you get 3 out of 10 because we can't grade the rest of the problem. So just be careful. Don't factor your homogeneous equations wrong. That's like a big source of like dumb mistakes. Okay. So let's see. One last Diffeq problem. Okay, so this one I thought I was like really cool and all. I was like, oh wow, this is a really sweet problem from a midterm. And then I went to the final exam and the dude just straight up ripped it from the final exam problem. So this is really final. This is the final from fall 2016, number 10. And it's the following. You get 4x squared y double prime plus y is equal to 24 root x ln x. Okay, so for those of you that attended my recitation, what method are we going to use? Reduction order y. Yeah, non-constant coefficients, right? I heard that being muttered. Also, the right-hand side, does it look pretty? Yeah, it looks gross, right? The ln x term, the root x term. Okay, so yeah, we're going to use reduction of order. I also forgot to give you a homogeneous solution, which also would have given it. So you're also given y1 is equal to x to the 1/2. Okay, so how are we going to proceed? We're going to use reduction of order. Okay. Quick question. Can we even use variation parameters on this guy? No, right? Okay, so don't try to be like, oh, let me try to use this cool method, variation parameters. This is non-constant coefficient, all right? So you can only use variation parameters if and only if it looks like y double prime plus some constant ay prime plus some constant by. That's like the only time you can use the variation parameters method. So that's why it's really limited. But with reduction of order, like anything goes, so we can use it here. So this is required for variation of parameters where a B are constants. So let's just say they're in R. Okay, so let's approach this problem then. Reduction of order, what we're going to do is, right, we're going to guess y of x. Right, so there's no yp guessing here. We just go straight to the general solution, and we guess y of x is equal to y1 of x times u of x. Right, so where y1 is just any solution that's given to us. So in this case, what would that be? So we guess y of x is equal to x to the 1/2 u of x. Okay, and the entire goal of making this guess is so that we can plug this guess into the original Diffeq, which means taking derivatives of y of x. So y prime at x is equal to, and here you have to be careful because you have to use the product rule because u is a function of x. All right, so this is going to be the following. So x to the 1/2 u prime at x plus 1/2 x to the negative 1/2 u of x. All right, and then y double prime, that's going to be x to the 1/2 u double prime at x plus 1/2 x to the negative 1/2 u prime at x plus 1/2 x to the negative 1/2 u prime at x plus or minus 1/4 x to the negative 3/2 u of x. All right, so just product rules over and over. So if you're unfamiliar with the steps in the recitation, I like explicitly label like step 1, step 2, step 3, step 4. But here we're just going to kind of do it generally. Okay, so here we go. Here's that. So now we need to plug it into the original Diffeq, which was the following: 4x squared y double prime plus y is equal to 24 root x ln x. All right, so what's the special trick to reduction of order? Yeah, we skip the u term. All right, so that u, anything that has a u but not a u prime or a u double prime, we just treat it like 0. So what does that mean? So this is 4x squared and then y double prime, right? So we essentially just ignore this guy and we just plug these guys in there. So we get x to the 1/2 u double prime. And then I'm going to make that notation change again where I'm going to drop the parentheses x because that's just extra notation at this point. So this is x 1/2 u double prime plus, and then 1/2 plus 1/2, that's an entire thing. So x to the negative 1/2 u prime. All right, and then we just completely ignore the u of x term. And then we add, well, it says we add y, but what is y? Y is x to the 1/2 u of x, which is a u of x term, so we don't need that either. So then we just really, this is really adding 0. And so that's going to be equal to 24 root x ln x. Okay, multiply this out. You get, this is equal to 4x to the 5/2 u double prime plus 4x to the 3/2 u prime is equal to 24 root x ln x. Okay, so now we're back, and this is a first order differential equation, right? It really, if you let u prime equal w, then this is really w prime, right? So it's really like a first order differential equation. so it's really a first order differential equation, but we're going to treat it with the u double prime and u prime terms. So how do we solve first order differential equations? Well, we have to use the integration factor technique. And in order to use the integration factor, I have to make sure that this term in front of my highest derivative, it has to be 1. Okay? So in order to make that 1, I divide everything by 4x to the 5 halves. I'm left with u double prime plus 1 over x u prime is equal to, all right, this is divided by 4, so that's 6. And then this was really x to the 1/2. So once x to the 1/2 divided by x to the 5 halves, that's really x to the negative 2 ln x. All right, so here's the integration factor. Right, integration factor is e to the integral of whatever this guy in front of the u prime is, which is a positive 1 over x. All right, so integration factor is positive integral 1 over x. So that's equal to e to the ln x, which is equal to just x. So for those in recitation, what's the left-hand side equal to? Yeah, derivative of integration factor times u prime, right? So we can skip a bunch of stuff, and this left-hand side is just the derivative of the integration factor, which is x times u prime. And the right-hand side, what's the right-hand side equal to? Yeah. Yeah, the right-hand side times the integration factor. So 6x negative 2 times ln x times x. All right, so if you're going to make this shortcut, just remember to multiply the right-hand side by the integration factor as well. In the recitation video, I kind of do it more step by step. But here, we're just going to do a little more of a shortcut. Okay, so really, let's just rewrite it. This is d dx of x times u prime, which is equal to 6x to the negative 1 ln x. And so now we need to take the integral of both sides to get rid of that d dx. So we get x u prime is equal to, does anyone know how to integrate 6x to the negative 1 ln x? Yeah, we can u sub this one away. So I guess we can't really call it u sub because we have a u. So let's call it a q sub. And so q is ln x, dq is 1 over x dx. Right, so this is really equal to the integral of 6q dq, which is 3q squared. So this is really 3 ln x squared plus some constant of integration c1. All right, we'll keep powering through. U prime then, divide everything. 3 ln x squared plus c1 over x over x. Right, so now we've isolated the u prime term. Now we're going to take integrals, right, on both sides again. And that's equal to u, which is, if you do the same q sub with ln x here, here you get ln x cubed. And then plus, this is, what, c1 ln x. And then you get a new constant of integration plus c2. Okay, so we're almost there. The last step then is y is equal to y1u, and y1 was x to the 1/2 times all this junk, so ln x cubed plus c1 ln x plus c2, and so There's your answer. Yeah.
I think in the other example of like a Cauchy over style question, there was also an ln x in the right-hand term. Is that like a pattern that will happen?
Yeah, so ln x, it shows up in the right-hand term a lot, but sometimes you get like really bad integrals with ln x. So I think I said in the variation of parameters video to have like the integrals like ln x and x ln x in your on your cheat sheet just in case it shows up. Yeah, and I mean you can always do it by parts on the spot, but I don't know how comfortable you're doing that on the spot. So that's like a really good, generally speaking, yeah, so maybe I'll just write it down, but like good integrals to look up. I mean, integral of ln x is equal to x ln x minus x plus some constant. Integral of x ln x, I forgot what this was. This is like 1/4 something. I look it up. This is in the integration. This is in the variation of parameters recitation. So this is in recitation 12. And then there's also x squared ln x, which has shown up on exams. Yeah, I can't tell you what that one is. Just plug it into Wolfram and see what it gives you. Okay. Any questions? All right, so why don't we take a quick break? If you're in my recitations, I have your homeworks up here, so we can do a big homework dig. And then when we come back, I'll talk about systems, and we'll get to systems questions.
somehow got picked to be the vice president of marketing, the undergraduate sports business stuff. I have no idea how. So yeah.
Let's see.
To be on my marketing committee.
I only have 4.
But then the lady forgot the key. John's from Shakespeare.
Worse.
Then,
Set 4 somewhere.
Yeah.
We don't have to. We did start first. Yeah.
Well, this is like homework number 2.
No, I just printed it out.
Oh.
Yeah, this is 4.
Were you still looking?
You can look through it. I didn't find it the
Yeah,
first
you can
go through. Okay, you can split it in half if you want.
Take one more minute and then we'll dig through these at the end.
Sure.
Okay. I'm gonna continue. Uh-oh. Okay, so let's move on to systems of Diffeqs. So with systems of Diffeqs, really it's just how well do you know your like eigenvalue, eigenvector stuff, and then there's a few other nuances on top of that. But if we take a look then at the first example, it's pretty straightforward. So this is number 4, which is from a midterm in 2015. We want to determine the general solution to x prime is equal to ax, and a is equal to 2, negative 1, 3, 2, negative 1, 3, 2, negative 1, 3. Okay, so right, you want to find the eigenvalues, eigenvectors. So what are the eigenvalues? Well, we're going to go back. For this one, if you try to compute it, it actually ends up being kind of a pain to calculate. So we're going to rely on some tricks to calculate eigenvalues, eigenvectors, right? So what is the first thing we're going to notice about this matrix A? Yeah. Well, it's actually not defective. But what makes you think that it might be defective? Yeah, so like all the rows are like, they're like repeated, right? The rows are repeated. So that being said, if the rows are repeated, what's the rank of this matrix? 1, right? So what's the nullity of this matrix? 2. Okay, so that tells me that the eigenvalue 0 has to show up. Yeah, how many times? At least 2. Right? Was it at least 2? Yeah, I think it was at least 2, right? But so we know that lambda has to equal 0 and has to equal 0. Actually, or was it then eigenvalues has to show up less than 2 times? Anyways, lambda equals 0 shows up twice. It works out fine. And then what's the last eigenvalue then? And it is? Yeah. It's not 2.
4.
Yeah, it's 4. Why is it 4?
The trace.
Yeah, the trace, right? The trace of the matrix is equal to the sum of the eigenvalues. So if I give you that 2 of them are 0, then what's the last one? It's 4, right? Because the trace of the matrix is 4. So does that ring a bell? Yeah. So the trace of the matrix is 4, so that's how we find the last eigenvalue since the first 2 are 0. Yeah, the nullity of this matrix being 0 ensures that lambda equals 0 has to occur at least twice. So we know that the multiplicity of 0 can't be 3 because the trace is not 0.
If you have like an upper triangular matrix,
Yeah.
aren't the eigenvalues? I mean the diagonals, the eigenvalues.
Yeah, but this is an upper triangle.
Oh, so you can't reduce it to make it.
No, you can't do that. You can't do that. You can't reduce it and then take the.
Okay.
That's not the same. Okay, so now what? So okay, we got 0, 0, 4. So lambda equals 4. Let's deal with this case first. So a minus 4I is equal to negative 2 or negative 2, negative 1, 3, 2, negative 5, 3, 2, negative 1, negative 1. Okay, so what's an eigenvector? Yeah.
1, 1, 1.
Yeah, 1, 1, 1. All right, so you have to get good at this again. All right, lambda equals 0. Well, that's just the original matrix, right? That's A minus 0, I, which is the original dude. So 2, negative 1, 3, 2, negative 1, 3, 2, negative 1, 3. I mean, here you can do a quick row reduction. Right? And so now we need to be able to get 2 eigenvectors from this guy. Otherwise, it's defective, right? Okay, so what are the eigenvectors associated with this? Yeah.
1, 2, 0.
Yeah, so 1, 2, 0. And then any others? Yeah. Negative 1, 1, 1. Negative 1. I don't have that one. I think, does that one work? Yeah, I think that one works, right? So that one works. I don't have it on here. So I have 0, 3, 1. Okay, negative 1, 1, 1 would work. Yeah, negative 1, 1, 1 definitely works. So. Okay, so those are my eigenvectors. And then, so the general solution is the following. It's x prime at t is equal to c1 e to the 4t times 1, 1, 1 plus c2 e to the 0t times 1, 2, 0 plus c3 e to the 0t times 0, 3, 1. And then e to the 0t is just 1. So this is really c1 e to the 4t, 1, 1, 1, plus c2 times 1, 2, 0, plus c3 times 0, 3, 1. And so, yeah, so this is just the general solution. I think that's it. So in this case, yeah.
So even with the repeating eigenvalue,
Yeah.
if it's a non-defective matrix, you don't have to add it.
Exactly, right? So I sent out an email about that to my recitations where I was like, if you get a repeated eigenvalue, as long as the matrix is non-defective, like it's fine, this is fine. Because the entire idea is that you want linearly independent solutions, right? And so this vector times a scalar is linearly independent from this vector times a scalar, right? Or this vector times e to the 0t is linearly independent from that. So as long as it's non-defective, it's fine. Okay? Which is different from differentially, like just ordinary differential equations, not in a system, because in that case you have to like keep on adding like extra t's to get linear independence. But here you don't have to do that. David, you have more questions?
Yeah, so can you get, are there multiple general solutions? Because like there are other eigenvectors.
Yeah, so like negative 1, 1, 1, right? So if we substituted 1, 2, 0 for negative 1, 1, 1, that's fine.
So like if we have a matrix that looks really weird like that with repeated rows, do you recommend like doing a trick to find the eigen?
Probably, yeah.
Yeah.
This would be quick. Right, it was on the last midterm too, right? Where you had like the matrix was like all threes, right? Remember that problem? And then same idea. Yeah.
I'm just still having trouble with the finding eigenvalues.
Okay.
Because is it true that a row-reduced matrix will have the same eigenvalue as? Because if you row-reduce it, you'll just get 2, negative 1, 3.
No, that's not true at all.
That's not true.
Right? Because let's take a look at this matrix. 1, 1, 0, 0, 2, 0, 0, 0, 1. Right? Well, the eigenvalues are 1, 2, 1, but if you row reduce it, you get 1, 1, 1 on the. Yeah, that's just not the same. So you can't just row reduce the matrix and take the eigenvalues. That's not going to be good. That's not right. Any other questions? This should have been like a simple one. I just wanted to show it just for the repeated eigenvalue. Yeah.
Kind of building up that question, so that would be done the eigenvalues.
Well, you just take. I mean, we'll do it here up next, kind of. But you have to take the determinant of a minus lambda I. right? And then you have to like mess around with that. But it's like kind of bad here because there's no like cofactor expansion that works nicely. You kind of just have to brute force it, right? But then if you notice that the nullity is 2, which means that 2 of your eigenvalues have to be 0, or at least 2 of them have to be 0, then that's like a quick way around it. Any questions? Okay, so let's move on. So number 5, spring 2015. Determine the general solution to x prime is equal to ax, and a is equal to 1, 2, negative 2, 2, 5, negative 2, 4, 12, negative 5. Okay, so for a question like this, there's no trick to this one, right? Like it's not, you don't see like tons of repeated rows or anything like that. So you kind of just have to find the determinant of a minus lambda I, and it's really bad in this case. So 1 minus lambda on the diagonal, and then 2, 5 minus lambda, negative 2, and then 4, 12, negative 5 minus lambda. Okay, this is really bad. Like, so I spent like 10 minutes trying to figure out this this determinant before I just gave up on it. But essentially, if you write it out, it ends up being the following: 1 minus lambda, right? So I'm just going to write out like the calculations you have to go through. So that's the first cofactor expansion. And then minus 2, and then here's the second cofactor expansion. Plus 8, and then the third cofactor expansion, minus 2, 24 minus 4 times 5 minus lambda. So like I try to be creative with like some like 1 minus lambda factoring tricks, but it didn't work out that nicely. And that's with me knowing what the root is anyways. So this simplifies magically to negative lambda plus 1, lambda squared plus 2, lambda plus 5. So in general, I think if we do have something that looks really nasty, I think we would just give you a hint on what the characteristic polynomial is. Yeah, because there's really no simplifying this thing. Okay, so that means lambda is equal to negative 1. Lambda is equal to, what's that middle one? Negative 2 plus or minus square root of 4 minus 20 over 2. So that's negative 1 plus or minus 2i. Hope I copied that down correctly, because I have plus 1 plus minus 2i on my sheet here, but that definitely isn't right given the characteristic polynomial. But anyways, that doesn't change too much of the final answer. So let's just proceed. Okay, so what can we do here? Well, we can take a look at lambda equals 1. And that's fine. So you get a plus I is equal to 2, 2, negative 2, 2, 6, negative 2, 4, 12, negative 4. Yeah. Okay, and then eigenvector. Any ideas? Yeah. Yeah, so I'm just going to flip it on you a little bit. I'm going to say 1, or negative 1, 0, 1? Almost. 1, 0, 1. 1, 0, 1. 1, 0, 1. Yeah, it was almost there, because you have the negative. You got the negative 2 at the end. Yeah. Okay, that's fine. And then here's where I think I actually made the mistake, because I do have the matrix over here. So I think this is actually a minus 2 lambda. And then this is a plus 2. And so this is a plus 1. Because, okay, so if we have lambda is equal to 1 plus 2i, then you get a minus 1 plus 2i lambda. A minus 1 plus 2i I. Okay, what is that equal to? So given the original matrix, you subtract 1 plus 2i from the diagonal. So this is negative 2i to negative 2. All right, this is 2, 4 minus 2i, negative 2, 4, 12, and then this last one becomes negative 6 minus 2i. Okay, this entire problem is just really bad calculations. That's what it is, because this is a terrible matrix to try to take complex eigenvalues for, or complex eigenvectors. So I guess you're going to see me try to do this now in real time. So what I'm going to do is I'm going to multiply the top row by I and divide by 2. So if I multiply by I, that gets rid of this negative 2, the negative sign here. So that just gets me 2. And then these become 2i, negative 2i, and then divide by 2. That should get me 1i and negative I. All right, then the rest of this is the same. Okay, so now what? Okay, so now I'm going to zero out that first column. All right, so this is 0. This becomes 4 minus 4i. And up here, this becomes negative 2 plus 2i. And then here I get 0. This becomes 12 minus 4i. And here I get negative 6 plus 2i. Okay, so we're just going to now factor out some constants from the rows to make them a little more manageable. 1i, negative I, 0. So I'm going to divide the middle row by 2. 2 minus 2i, negative 1 plus I. And then the bottom, I'm also going to divide it by 2. So 0, 6 minus 2i, and negative 3 plus I. Okay, so what to do now? What I want to do now is I want to get a pivot here that I can work with. Okay, so I'm going to have to multiply that by the complex conjugate. So I'm going to take this row. I'm going to multiply it by 2 plus 2i. And so what I get then is the following: 1i, negative I, 0. All right. A thing multiplied by its complex conjugate is just, it's this squared plus this squared. All right, so when you have something multiplying by its complex conjugate, it's just 2 squared plus 2 squared. That's going to be 8. And then now I actually have to calculate what negative 1 plus I and 2 plus 2i get me. So this is negative 2 minus 2i plus 2i and then minus 2. So that's minus 4. 0, 6 minus 2i, negative 3 plus I. More reducing. 0, 1, negative 1 half. 0, 6 minus 2i, negative 3 plus I. So finally, all I have to do is try to zero out this guy on the bottom. But you'll realize that negative 3 plus I is negative 1 half times 6 minus 2i. Okay? Right? Because if you multiply the A term by negative 1 half and the B term by negative 1 half, you get exactly what you get. So that means the last row gets killed off, and so I'm left with this. All right. And now we need to look for an eigenvector. So row 2 tells me what my eigenvector, like what values my eigenvector can be, right? So so now we need to look for a V2, and so row 2 tells me what the second and third entries are, and that should be 1 and 2. Okay? So second and third entry should be 1 and 2. And then if you plug that into the first row and you do the dot product, you see that I have I minus 2i. So that means I need another I, and I get it there. Okay, so after we've gone through this arduous process of finding just the eigenvector in the complex case, what we're going to do now is, well, we need to write the general solution. Right? So the general solution is the following. It's going to be C1 e to the negative t times 1, 0, 1. Okay, so that's the e to the negative 1 eigenvector, right? That's this eigenvector right here. Okay, and now what we need to do is we have plus C2 times something and plus C3 times something. And so we need to find what C2 and C3 are based off of that complex eigenvalue and complex eigenvector that we found above. Okay, so how do we do that? Well, this eigenvector, I12, right, it corresponds to 1 plus 2i. So essentially, right, we have e to the 1 plus 2it times I12. Okay, so that technically would go in here, but it doesn't make any sense to put it in there because you can't have i's in your final solution, right? You can't have i's in your general solution. So we have to do something to this. All right, so you got e to the 1 plus 2it times I12. So e to the 1 plus 2it is equal to e to the t e to the 2it times I12. And so that's really e to the t. All right, and now e to the 2it is cosine 2t plus I sine 2t. And then we also want to factor out this guy into an imaginary and a real part. So the real part is, what's the real part? Just for the I12 vector, right? Because we got to like split that one up.
0, 1, 2.
Yeah, 0, 1, 2. And then we have I times the imaginary part, which is 1, 0, 0. Okay, so now we have this, right? This guy, e to the 2it is that, and then this mess got split up into a real and imaginary part. So now what we have to do is that we have to FOIL it. So that's equal to, so e to the t multiplies all of this, and you got cosine 2t, 0, 1, 2, so that's the first, and then you got the outer plus I cosine 2t, 1, 0, 0. And then the inner plus I sine 2t, 0, 1, 2. And then you got the last, which is actually minus sine 2t times 1, 0, 0. Okay, so now we're done, or we're pretty close to being done. What we need to do is we need to take the real parts. All right, so these parts are real because they don't have an I in front of them, and that's one of the solutions. So e to the t multiplied by all this stuff. So we're going to take e to the t, right, and then you have the two real parts, which is cosine 2t, 0, 1, 2, plus, or minus sine 2t, 1, 0, 0. Okay, so that's one of the solutions. And then the other solution are going to be the sine terms, or the imaginary terms with the i's in front. But we have to drop the i's, so then this is going to be e to the t, and what is this? This is cosine 2t, 1, 0, 0, plus sine 2t, 0, 1, 2. Okay, and then the general solution is all of this. Any questions?
Why do you just drop the I?
You drop the I. So one way you can think of it is that the C3 constant term eats the I. Okay, that's one way you can think of it. The other way you can think of it is like the original matrix has no i's in it, right? The original coefficient matrix doesn't have an I in it, so you can't have an I in your final answer. Because it doesn't make sense. It can't, like, the I won't disappear if you take derivatives. So that's why you can't have it at the end. Yeah?
So we don't need to plug like lambda equals 1 minus 2i and then find it.
Yeah, so you don't, because what will happen is that you get the same thing. Any other questions? Okay. So finally, we come to an example that I try to avoid this morning, but we're going to have to do it now. X prime is equal to ax, and a is equal to 2, negative 1, 1, 4. Okay, so stop me along the way if any of this doesn't make any sense, because it's the first time that we're talking about this. And it's the case where the matrix is defective. So what goes on? Determinant A minus lambda I, all right, is the following: 2 minus lambda, negative 1, 1, 4 minus lambda. Okay, and so this one's pretty easy to actually multiply out because it's a 2 by 2. So there's your characteristic polynomial. And this is lambda squared minus 6 lambda plus 9. Okay, so we get lambda equals 3 with multiplicity 2. Okay, so here we do the following. We still proceed as normal. Lambda equals 3. All right, and here's a minus 3i. It's equal to negative 1, negative 1, 1, 1. And here, it's really tempting to find an eigenvector, but we're not allowed to. here's the following reason why. So what you should do instead is, what's the nullity of this matrix? Or what's the rank? Let's do that first. That's easier to do. The rank is 1. Okay. So the rank is equal to 1. So that means the nullity is equal to 1, right, by the rank nullity theorem. Okay, remember that? Okay. What's the problem? The problem is the multiplicity of lambda equals 3 is equal to 2. Okay, so what's wrong? Yeah, Mark.
Since the nullity is 1, wouldn't you expect 0 to be an eigenvalue 1 time?
Well, this is the nullity of A minus 3i, not the original matrix. Yeah. Okay, that's exactly what it is, right? So we need 2 eigenvectors, right? So multiplicity 2 says that we need 2 linearly independent eigenvectors. Right? Because that's what the multiplicity means, right? So because lambda, right? Lambda is really equal to 3 and then 3, right? So then each lambda has to be associated with its own eigenvector, which is what we saw in the first example, right? Where lambda equals 0, they're associated with its own eigenvector. But the nullity being 1 means that there's only one linearly independent eigenvector. Well, there's only one linearly independent vector in the null space. Oh boy, the null space is back, of A minus 3i. And remember what an eigenvector was. An eigenvector satisfies A minus lambda IV is equal to 0, right? So V is your eigenvector. So V has to be in the null space of A minus lambda I, right? So in our case, our eigenvector has to be in the null space of A minus 3i. But there's only one of them. That's what the nullity means. Okay, so what do we do? Okay. So there's this whole section that we skipped in chapter 7.6. It's called Jordan Canonical Form. It's an optional topic, but like almost every other semester we covered it, and we didn't this semester. So I'm not going to introduce it, but I'll tell you what the general idea is. The nullity, you can think of it another way. The other way you can think of the nullity is the number of cycles or blocks. Okay, so this is the number of cycles or blocks associated with lambda equals 3. So what does that mean? That means that, remember when you did A is equal to S ds inverse, and you had, so for a 2 by 2, this would have been like V1, V2, lambda 1, lambda 2, right? And then this is like V1, V2 inverse, right? So that was S ds inverse, right? But in this case, we can't form S. Okay? There's no possible S that can be made. So instead, we write A is equal to SJS inverse. And what does this mean? The number of blocks tells me that how many blocks are in this matrix, in the J matrix. So now I'll have something, right? And here, so in our case, we'd have 3 and 3. Okay? But this says my J matrix has one block. All right, so what does a block mean? One block just means that this J matrix, right, you can draw one block in it. All right, and so we have to fill out the block. And how do we fill out the block? We do it by putting a 1 in the upper triangle region. And there's a 0 down here. All right, so that's what it means for there to be one block. Right? And so if it were diagonalizable, the nullity would be 2, and you'd have 2 blocks, which is fine because your 2 blocks would have just been these 2 blocks. Does that sort of make sense? Yeah.
What happens if there's if this wasn't 2 by 2 matrix?
Yeah, so that's the reason why he only said you had to worry about 2 by 2 matrices, because once you go to higher dimensions, like 4 by 4s, which is like what they had to do last year, you kind of have to just guess and check with like your block sizes. It's really bad. Yeah.
Wait. Why is that like one block versus then you said like you could just box the 3s and those are 2 blocks?
Right. So if you box, if you box the 3s, so first of all, a block has to be on the diagonal. So for example, if this were like a 5 by 5 matrix, right, this would be 2 blocks. If this were a 3 by 3 and this were a 2 by 2, like it has to be on the diagonal. All right. So another way you could do blocks is you could have 5 blocks on the diagonal, right? Or you could have something like a 2 by 2 block, a 2 by 2 block, and a 1 by 1 block. Right? So all your blocks have to be squared, and they have to be on the diagonal. So when you have a 2 by 2 matrix and you only have 1 block, then the block has to be the entire thing.
So what does that like imply? That like why does that imply that it's like?
So we're getting there. We're getting there. We're getting to like what this entire thing means. Okay. So the whole idea, the whole thing I'm trying to say is that the nullity equals 1 means that your center matrix has only 1 block in it, and that 1 block is the entire thing. All right, so this is a 2 by 2 matrix. Right, this block is 2 by 2. Okay, does everyone, okay, so let me repeat that again. Nullity is 1. Okay, nullity being 1 means that when I write this as SJS inverse, because it's defective, right? So this is this is non-defective, this is defective, right? When it's defective, you have to do all this block shenanigan stuff, all right? The nullity equals 1 means that the center J block has only 1 block inside of it, all right? And since the center block, the block must be square, so it has to be 2 by 2. There's no other size it can be. Yeah, and you just automatically fill in 1 and 0. If you have a 3 by 3 block, it looks like something like this. So you have lambda, 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 right? And then you would put 1, 1, and then that's it. So that's kind of what you do. You put 1s right above the diagonal. So that's how you fill in blocks. Yeah.
Just because we only have to do 2 by 2s, we're always going to have a 1, 0. That's how you just.
Yeah, for a 2 by 2. Yeah.
If it was 2 blocks for a 2 by 2, would you still have the 1, 0?
No, right? Because then there's no empty space in your block, right? Because so if I had 2 blocks, it'd be a block around the 3 and another block around the 3, right? Because those would be 1 by 1 blocks. But then you don't have empty space per se.
What would you put in the other?
They would just be zeros, right? You would just have a diagonal matrix because it would be diagonalizable if it had 2 blocks. Does it make sense? Because what's the condition for this to have 2 blocks? The nullity is 2, but then that would be equal to the multiplicity, so they would be diagonalizable. So then we wouldn't have to worry about this entire thing here, right? Okay, so in the 2 by 2 case, this is the only thing that can happen, yeah.
So you just have the 1 above
Yeah, exactly. Yeah, so 1's above the diagonal. That's essentially what it is, right? See this 3 by 3 example on the side here? Yeah. Okay, so why do we make a big deal about these blocks? The reason is because you look at the size of your largest block. All right, in this case, it's 2 by 2. Take the size of the largest block. All right, in our case, it's a 2 by 2, right? And then now you want to raise a minus lambda I to this largest power size. All right, so in our case, you have a minus 3I, and since the largest block is a 2 by 2, we're going to square it. All right, so that's the entire deal about these blocks. All right? So you can tell for even larger matrices, it gets really annoying having to deal with like the block sizes. But for a 2 by 2 and it's defective, your block size is automatically going to be 2. Okay? So what is that? Well, okay, so remember, this is equal to then, what was it? It was like -1, -1, 1, 1. All right, so we square this. And we get the 0 matrix. Yeah.
How would you do this without using this whole block?
You can't. Right. So this is like, so this part, it's called Jordan. So this block form, it's chapter 7.6. It's called Jordan Canonical Form. All right. So usually we spend like a week on it, but this is like an optional topic.
So would this type of question be fair game on the exam?
He said it was fair game on the midterm, or at least in my email, because you guys covered it in lecture yesterday.
He gave us like a format to put the general solution in.
Right. Oh, so I guess I'm going to derive it here then. So this is kind of like the derivation behind that, because for a 2 by 2, like it's forced, like you can see everything is forced to be like this block size, right? So I mean 3 by 3s aren't going to be on the exam. That's really plug and chuggy, but. Anyways, this is like the derivation, because he just told me that you're gonna have to, like defective matrices are fair game for the exam, and so this is how I taught defective matrices last year. So this is kind of what I'm doing now. So okay, this is the same thing. So now you get this thing, right? You get the 0 matrix. So this is a minus 3I squared. Okay, so now we need, and this is a minus 3I, right? We need a vector, all right? We're going to call it V underscore G, or V subscript G, such that a minus 3I squared equals 0, but a minus 3I, or a minus 3I squared times the vector Vg is equal to 0, but a minus 3I itself, not squared, times Vg is not equal to 0. Okay? And we call Vg, this is a generalized eigenvector. Okay, so here's a minus 3I squared. Here's a minus 3I. So what is a vector multiplied on the left by a minus 3I squared gets me 0, but multiplied on the right by a minus 3I gets me not 0. almost any vector. So does anyone want to try give me one? No. Okay, so you give me the one that doesn't work, I think. Wait, hold on. 1, 1, 1, 1.
0, 0 also doesn't work.
Yeah, no, 1, 1 doesn't work. So 1, 1, 1, 1 is like the only one. I'm pretty sure 1, 1 doesn't work. No, okay, 1, 1 does work. Okay, so let's just roll with it. 1, 1 is okay. Yeah, 1, 1 works. 1, 1 works. 1, 1 works. Negative. So 1, negative 1 doesn't work. Okay, so for example, right, let VG equal 1, 1. All right, a minus 3i squared VG is equal to the 0 vector times 1, 1, and that's equal to the 0, or that's equal to 0 vector, so that's okay. A minus 3i times VG is 1, or negative 1, negative 1, 1, 1, times 1, 1, and what is this? This is negative 2, 2. Yeah, for a 2 by 2 it will be, which is like the entire point of like forcing it to be 2 by 2. Yeah, for 2 by 2 it has to be. Okay. Okay, so now what we do? So let's write what we have. We have VG is equal to 1, 1. All right, and the other thing that we really care about is this guy, a minus 3i VG. So a minus 3i VG is equal to negative 2, 2. All right, so these are the two vectors that we really care about. So, and the reason is the following. Because now x of t, all right, is equal to the following. It's C1 e to the lambda t times a minus 3i VG plus C2 e to the lambda t times V times t a minus 3i VG plus VG. So what we have is then C1 e to the 3t negative 2, 2, all right, because that's that guy, plus C2 e to the 3t t times negative 2, 2 plus 1, 1. Okay, so that's the general solution. Okay, so why is this a mess? Well, this whole cycle thing is a mess, just like introducing it for the first time. What I want you to notice is that, does anyone see what negative 2, 2 is? Does anyone notice what negative 2, 2 is? It's an eigenvector, right? It works. Like, so negative 2, 2 works as an eigenvector, right? If you look at this matrix, right, if you take negative 2, 2, right, that's an eigenvector, right? So a minus 3i VG, this is an eigenvector, all right? And the reason why we couldn't just pick an eigenvector initially, it's because this eigenvector is generated by VG. All right, so VG is the generalized eigenvector that generates an eigenvector. So we can't just we can't just pick an eigenvector up here. Like, it's really tempting just to say -1, 1, but then you have to pick the correct generalized eigenvector. Otherwise, it's not going to work. It's going to be wrong. Yeah.
Can you work backwards and start with
You-
minus I VG equals your eigenvector and then find
Yeah, but then you have to invert a minus. Well, can you even do that? You can't invert that because the determinant is 0. So yeah, I would just stick to. I mean, you can try, but I would recommend squaring, taking some generalized eigenvector and getting it. So like the whole formula that you have to like solve these kinds of defective matrices, like if you go home and you like apply that formula here, you should end up with a very similar answer. Yeah.
So the Jordan Canonical matrix is not important. It's only important for the finding the power solution.
Yeah, exactly. So what actually ends up happening is, you know, this whole SJS inverse stuff. Here you would actually put the eigenvector that's generated. So this would have been -2, 2. And here this would have been the generalized eigenvector, which we picked was 1, 1. Right? So this would be VG, and this would be A minus 3I VG. And then here would be -2, 1, 2, 1 inverse. So this is the Jordan Canonical Form. But it's not important because what's more important is figuring out how to even get the generalized eigenvector.
It's like
Yeah, yeah. Yeah.
So you talked about that derivation on the test, right? Like, what do we know from this that we have?
What you need to know is essentially here is that if you recognize it's defective, right? Square A minus lambda I, right? Find some generalized eigenvector that makes the squared matrix 0, but makes the regular matrix not 0, and then generate that eigenvector using your generalized one, and then from there just plug it into that form right there. So I guess this is actually wrong. This should have been A minus lambda I, and this should have been A minus lambda I right there. But yeah, so you just have to generate your eigenvectors and your generalized eigenvectors. So yeah, I do have videos about this online if you're wondering what's going on.
You said that like it's always going to be a 0 matrix when it's squared.
Yeah, for a 2 by 2. Because the generalized, the matrix that gets you the generalized eigenvector has to be nullity 2. So a 2 by 2, yeah, so a 2 by 2 nullity 2 matrix is the same matrix.
So we just pick VG as something that isn't multiplied isn't.
Exactly.
Because like it's always other than
Exactly.
I found in my notes when he went over, he had one example of 2 by 2.
Yeah.
He just wrote out this form on the board. C1 e to the lambda t, v1 plus c2 e to the lambda t, then vo plus tv1. He said we just need to pick vo and v1 such that they're a basis for our.
That's not necessarily correct.
That's like someone asked it and he like, oh, we'll get back to that.
Yeah, that's not. This is like the correct way. This is like the right way. If you pick a basis, no, that's not right.
You just didn't like.
No, you can't just pick any random basis. That's not right. That's wrong.
Like, to add to that,
Yeah.
how are they going, like, they're not going to expect us to know how to predict defective matrices on the final if we're not going to have none of them.
Yeah, that's what I thought.
We really didn't do anything.
I know you guys didn't do any of this. I like went up to him, like we were at a meeting, and I was like, yo, are you gonna even cover this? And he was like, I don't know.
Yeah.
And he ends up covering it on Tuesday, and I was like, really? So, or he covered Thursday, right? Yeah, see, I knew this was gonna happen because covering this stuff, everyone's just like, what the hell is this?
Maybe tell them not to put it on the midterm.
We'll see.
Isn't the final across the whole department?
Yeah, so the final might have this. That's like the big thing. All right.
So did other professors come to the building?
Yeah.
They said no.
Yeah.
He said no, but if he's covering it now, it probably meant yes.
Okay.
So
we should learn the Jordan Canonical Form.
yeah, I don't see. You have one lecture left on Thursday. I don't know what he's gonna cover. If he covers, so he can cover like, there's like systems where it's like there's like a chapter in like 9899 where you just like look at like pictures of spirals and shit like that. So like that's usually on the exam, but then if he like emphasizes this stuff, then that's not good because then that means we're gonna have to talk about this a lot more in a not 2x2 case. I mean the 2x2 case is it's like the simplest case because you square the A minus lambda I matrix to get 0. Pick your favorite vector that's not an eigenvector.
Yeah.
So yeah, I mean I'm gonna have examples. So I need to update the practice problems to include 2x2 examples of this. So we'll see those.
Thank you. This is helpful.
Yeah, I think so.
Yep. Any other questions?
Yeah, so I was just confused on like the system of linear equations. But yeah, so when we have so when we get something that's a complex value, and like I understand that you do like the real and like C2 times real and C3 times imaginary. Yeah. So why do we only use like one of the conjugate pairs and not the other one?
Because you end up getting the same thing. If you remember remember the complex eigenvectors, remember the whole trick about getting complex eigenvectors is that if we have one of them, we have the other one.
Well, don't you have the other one just because you just add the minus sign?
In front of the i's.
Yeah.
Right? But what are you doing here? You're just adding minus signs in front of the i's, right? So the other one would have been, so here you have, so you have e to the minus t, it's actually 1 plus 2i. So this isn't actually e to the minus t. I like changed it. I'm just pointing out.
Isn't this from the first one?
Yeah.
The non.
Sorry. Yeah, that's good. Never mind. Yeah. So here.
So this is like the times real times imaginary.
Right. So, let me see. So you're asking why don't we use it? So we have e to the 1 plus 2i, right?
Yeah.
So
and that's
let's say we had e to the 1 minus 2i.
Yeah.
Okay. What happens? This is a minus i now.
Oh, and then the minuses will just.
And the minuses and just canceling.
Okay.
So
okay.
Yeah. So is there like any reason for this form, or you just kind of have to memorize that one? Like that, like looks normal to me.
Okay.
But that with the plus, it just.
The t two
like
two
for this,
plus.
yeah. Like
Yeah. I mean. I would. So, I think I have a video on defective matrices. I don't know which one it is.
I'm about to learn Jordan Canonical Form. Yeah, bro, you can't do these questions without it.
Yeah, so there's a video on it. I think more or less you kind of just have to like know what to do.
Okay.
Yeah. I don't think